Good afternoon, everybody. Today we will discuss the next topic of chemical kinetics, that is the second order reaction. We can classify the second order reaction into two different types. One is the chemical reaction in which only one reactant is involved and we are using two more of the same reactant in the chemical reaction. So this is an example for the second order reaction. And the next variety is we are using two different type of the reactant in the chemical reaction. So let us discuss the two different variety in detail. Consider the first variety, that is 2A gives product. Here we can see that only one type of reactant is present and 2 moles of reactant A is involved in the chemical reaction and to form the product. So the initial concentration of the reactant capital A is small a, and after a particular time interval t, the concentration of A is reduced to A minus x. So how we will write the rate expression? Rate equation is equal to, here the change in the concentration of A is only x at the time t. So we can write dx by dt, that's equal to K2, that is the rate constant, into concentration of A to the power 2. Here the concentration of A is reduced to A minus x. So our equation become dx by dt, that's equal to K2 into A minus x whole square. Then after the integration, we can write the integrated rate expression for the second order reaction having only one type of reactant is equal to K2 is equal to 1 by T into x divided by A into A minus x. This is the rearranged version. Whereas if before rearrangement, we will get the equation become K2 into T, that's equal to 1 by A minus x minus 1 by A. This is the integrated rate expression for the second order reaction having only one type of reactant. And we are considering 2 moles of reactant A in the chemical reaction. So next we are moving into the next type of second order reaction. That means we are using the two different type of reactant such as A and B involved in the chemical reaction, and after the chemical reaction we will get a single product, maybe single product or multiple number of the product. Consider in this equation reactant A react with next reactant B, that is an entirely different from A, and to give the product. So initial concentration of the reactant A is small a and initial concentration of the reactant B, capital B, is small b. After a time interval, let us t, concentration of capital A, reactant A, is reduced to A minus x and concentration of the capital B is reduced to B minus x. So how we will write the rate expression for a second order reaction having two different reactants? So we can write like this, dx by dt, that is the change in concentration of the reactant, that's equal to K2, that is the rate constant, into concentration of A, that is here it is A minus x, and concentration of the B, here it is B minus x. Then after the integration, we will get the integrated rate expression for the second order reaction is K2 is equal to 2.303 divided by T into A minus B into log B into A minus x divided by A into B minus x. So we have to by heart both the equations, integrated rate expression for the second order reaction having one reactant and integrated rate expression for the second order reaction having two different varieties of the reactant. Now let us move into the derivation of the the second order reaction having only one type of the reactant. So our equation is A gives product, 2A gives product. So we write the rate expression as dx by dt is equal to k into a minus x whole square. Then for the integration we have to take the x term on one side. So consider we have to move the a minus x term to the left hand side. So our equation become dx by a minus x whole square, and we have to move the term dt to the right hand side. So our equation become dx by a minus x whole square, that's equal to k into dt. And we are measuring the small change at a particular interval. For a chemical reaction we have to measure the entire change during the chemical reaction. So we have to integrate the equation. So integral dx by a minus x whole square, that's equal to integral k into dt. After integration, our term become 1 by a minus x, that's equal to kt plus c. This is our integrated rate expression for the second order reaction having only one reactant. Now we have to find out the integrated rate constant c. For that we have to substitute t is equal to 0. That is, we are measuring the initially the concentration of A at time t is equal to 0. So our x becomes 0. So the equation become a by 1 by a, that's equal to c. So substitute the value of the c in the above equation. Our equation become 1 by a minus x, that's equal to kt plus 1 by a. After rearranging, we will get kt is equal to 1 by a minus x minus 1 by a. If you are moving the term t to the right hand side, our equation become k is equal to 1 by t into 1 by a minus x minus 1 by a. This is the integrated rate expression for the second order reaction having only one type of reactant. I hope that you understood the concept. Thank you.